This is the Lorenzana piece, which ended up being retracted. And there's a particular hypothesis. I'm an outsider to this field. Doesn't seem like a staggeringly plausible hypothesis to me. Does higher physical altitude lead to more pro-social behavior? Because individuals think of some analogy between the moral high ground and sort of the physical high ground. That's the kind of underlying idea. So what ends up happening is participants were in a kind of theater. Some were led up onto the stage and asked to make decisions. Others were led down into the orchestra pit to make decisions, and others stayed at the same level. And the idea is somehow that if you're up on high, you will behave in a more magnanimous, pro-social fashion. This is the test. And the way you're more pro-social, and again, you're making food for other participants, and if you use less hot sauce, that means you're being nicer to them. So this is the study. And if you use more hot sauce, you're less pro-social. I don't know what kind of hot sauce it was. Here in California, we care about that. So there are different treatments. There's the high ground, there's the control, there's the low ground, and then there's different types of behavior that's being studied. And this is a reproduction of the table in the original paper. Again, this is the actual height, high, low, control, and then these are the different outcomes. And he's going to focus on these three. This is the grams of hot sauce that you used. So, this is your compassion. If you take the moral high ground, you use fewer grams of hot sauce than if you were down in the orchestra pit. So this is the idea. And what you can see, and this is what Uri says caught his eye, is that if you look at the variability in the data, these are standard deviations. This is the sample standard deviation. They look really similar for pretty small samples. And then the same thing for these, and then the same thing for these down here. And so his point is, wow, those look really similar, like sample standard deviation. Like a sample standard deviation is itself a random variable that has a standard deviation, that has a sort of expected amount of variability. And with a relatively small sample, that random variable, the standard, the sample standard deviation, should be expected to have some spread, and these don't have much spread. So what does he do? At first, he didn't have the raw data, so he basically assumes the outcome is distributed in a certain way, assumes it's distributed normally as a starting point. Later on, he's going to get the raw data, so he doesn't have to even worry about that. He says, okay, I kind of know what the mean is in each arm. He's going to compute the pooled standard deviation across the three arms, kind of imposing some artificial commonality there. Doesn't even know if that's true. And take 100,000 simulated draws of the data and get a sense for what the distribution of standard deviations, of sample standard deviations, looks like. That's the idea. So it's actually pretty straightforward. And then he's going to compare the standard deviation in the paper to this distribution of sample standard deviations that he simulated. So what does he find? He creates this, he has these 100,000 simulations, and, he simulates the distribution of sample standard deviations, and they have a nice shape, as we'd expect them to have, and it turns out that the Sana et al. Piece is way, 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 way out in the tail. So the p-value here, this is pooling across those three different outcomes. The p-value is 0.00015, 15 out of 100,000 cases. So it seems really unlikely that these data are randomly generated from random samples, right? That's the first conclusion. Then he received the raw data, and after receiving the raw data, he can do the same thing, taking draws, basically random samples with replacement from the existing data to create the same distribution, effectively, of sample standard deviations. So he does that, and you get almost the same p-value. And again, it's extremely unlikely. So, and in many ways, this is preferable, this approach, in case the outcome isn't normally distributed, in case there's some weird correlations between different outcomes. Like, you're going to capture it when you're taking draws from the real data, these draws with replacement. So this is a preferred method, and you get the same answer. what Simonson then does next is he compares this kind of standard deviation of sample standard deviations. I love it. In this study to other published studies that have commonalities, that use a common outcome measure, that look at similar things. And so what he actually looks at is studies that cite the same papers that the Sana et al. Piece cited, like kind of studies that are being drawn from the same literature. And he compares this psi. Psi is the normalized standard deviation of sample standard deviations. And the Sana et al. Results are clear outliers. So this is the psi term on the left-hand side here for these three kind of sub-studies, arms 2, 3, and 4 of Sana. And you can see there's just very little variation in the sample standard deviations. But then there's other types of studies that have commonalities. For instance, there are studies that use hot sauce. And there's a hot sauce subliterature. And in that subliterature, there tends to be a pretty large psi. Psi is, 100 to 200%, not 12%. I mean, it's just like order of magnitude off in the amount of variability. Again, like a bad cheater was Sana. There's other studies, time on some unsolvable task. There's other studies that are kind of public good studies contributing to a common resource. They all have tons of variability. And of course, all these studies, none of them are anywhere close to Sana et al. It just looks like this is not real data. Simonson then decided to look at several of Sana's other papers, and all of them had this property of too little variance in sample standard deviations. So it was a systematic pattern. Kind of looked like he was sort of making up his data probably the same way. And then if he looks at other statistics, so for instance, one statistic he looks at is the difference between minimum and maximum values in a sample. It turns out that's a really volatile characteristic. But the difference between the max and the min in all these arms is almost exactly the same. It's just very weird-looking data. So he kept looking, and he kept finding funny patterns. So he was almost certain that the data had been made up. And since then, a large number of publications. I'm not sure if it's all of Sana's publications, but a large number have been retracted. He's resigned, etc.